Our universal law of gravity, gravitational force law, is G, I'm going to use a little m and a big M over r squared, and it is a vector, so it points along the line from the object acting to the object being acted on, and it's an attractive force, so that means it's minus. So r points away from the acting object, which I'm representing with big M, and it pulls the smaller object towards, or the other object towards it, so that's where the minus sign. Okay, so our question is, here's a force. Let's say I try to get a rocket ship and shoot it off into space, and give it just some big explosion, and it shoots off into space, but it's slowing because the Earth is pulling back on it. I'm going to ask, well, what's the work done by this force? But more interesting, I could say, what's the potential energy between two objects that are interacting via this gravitational force? And we can represent this interaction with a potential energy. So remembering that our potential energy difference, or the change of potential energy in a system, is equal to the negative work internal, where I use internal represent this, I'm including the acting object in my system, and so it's the work done inside my system, work done by one object of my system on another object of my system, and that is the same thing as the negative potential energy change from that interaction in my system. Okay, well, work, we remember that, is force dotted with some displacement, which I'm going to choose R here. And we just need to plug this in to that equation and then consider a change in position. Now, the best one is to do this. Let's suppose, like, here's our Earth, or just the main gravitating body, okay? And our object, let's say, starts right here, or it's moving right there at some position R. Okay, let's call that R initial. And we send it way out to infinity. So R final equals infinity, super far away. Okay, now we'd expect that if this was, I launched something and it doesn't have any more fuel and it's just gliding away from the Earth, it's going to eventually slow down and stop. Okay, it may take a really long time, a really far distance, but it should eventually stop if this is the only thing acting on it. Pulling it back, so it should eventually stop. But the question is, if it's super crazy far away, then the interaction energy should be also zero. So we could say that U here, by our definition, is zero. Okay, that's going to be our choice of a zero. Remember, your potential energy is your choice. I'm going to say the potential energy at this position far away is zero. Okay, well, what would be the potential energy here? What is the potential energy at this distance? And I'm going to leave it as R without a subscript, because once we solve for it, well, we can change whatever R it is. So we can figure out what is the potential energy when you're a certain distance away from this object. Okay, now what we're going to do is we're moving this object way out there. So we're choosing our direction for R hat. It's away. So this dr points away. Okay. Now the force points towards it. So F points this way, but our dr points that way, which means they're opposite each other, which means the dot product gives me a cosine of 180, which is -1. So I can now write my potential energy change is a negative of a -1. So I get a positive here, F dr. I'm going to go from my initial distance to my final distance, which is infinity. All right, well, now I just plug in this as a magnitude. I've already taken care of its direction, so I don't care about that minus sign. I've already chosen it by saying it's this way. So I just plug that in, and I'm going to go ahead and pull out the constants right away. The G, M, and M, they're constants. And all I get, I get an integral from initial to final of dr over r squared. Okay. Now that's not too hard of an integral. I can do that one. That's going to be equal to a negative negative 1 over r, where I evaluate this at the final and then the initial case. So let's go ahead and come back up here. So now this delta u is equal to a negative gmm, and I get a 1 over r final minus 1 over r initial. Okay, that's how I evaluate this at the endpoints. But our final is infinity. 1 over infinity is 0. So I can cross that out. And I have a negative and a negative. We have gmm over r initial. Okay. So that's the change in potential energy as I move from my initial to my initial to my final. So this is final minus initial. So let's go ahead and rewrite that. This is u final minus u initial equals gm big M over r. I'm just going to leave this as, well, no, I'll do the subscript at this point. Okay, but what did I say about u final? What is the potential energy way out here? That's my choice. Remember, that's my choice, but I choose it to be 0, which seems reasonable. If something's crazy infinitely far away, then it seems reasonable that the interaction energy is 0. There's not much of an interaction right there. And so I choose this to be 0, which means I just flip that minus sign over, and now I'm going to drop that subscript and say this is g m over r with a minus sign. Okay, so this is the gravitational potential energy between two objects of mass m and big M when they are a distance r apart. Their centers are a distance r apart. Okay. Now that minus sign may be interesting. It's like, well, hold on. I remember that our potential energy was mgh, and I'm going to show that in a second. But this still makes sense. The higher I go, the further apart I get from this object, between these objects, the greater the potential energy. So let's plot this to see that. If I plot potential energy as a function of distance here, okay, when I'm super far away, when r is super big, this whole thing goes to 0. So I'm approaching 0 here. Now when r gets to 0, this becomes negative infinity. So I'm way down here, so it's approaching negative infinity. And I get a 1 over r relationship, but inverted. So that's what I get. Now granted, I drew this a little too close. It doesn't actually get to 0, it just approaches 0. So when I am super far away, my potential is very big and negative. When I get closer, it becomes less negative. Okay, and so my potential energy is getting closer to 0. Okay, so it does work out. Sorry, I said that backwards. I was confusing myself on my minute. I'm glad I caught myself. When r is really big, we're close to 0. Okay, all right, but that's bigger than negative. Okay, so when r is really small, I'm super negative, and as I get further away, you can basically say my height is getting bigger. I'm getting less negative, which is a bigger potential energy. So this is consistent with our other understanding. Now this is a really powerful relationship we can now use, very much like we used conservation of energy before, only that what we've done so far is for only things close to the surface of the Earth where potential energy due to gravity was mgh. Well, now we can apply the same principles only with planets and asteroids and things that are really far apart, or potential energy of a landing module on Mars. Okay, we don't have the same G anymore, so we have to play around with that. Okay, so this works for all cases. Now it is, it's kind of hard to see that and say, well, that doesn't look anything like mgh. And even though I've shown that it does get bigger like mgh, with increasing distance. Let's go and see how that becomes mgh. Okay, so let's take a look at the change in potential energy. So if I'm at the surface, that's Re, and if I'm somewhere above, that is Re plus h. Okay, so if I'm at the surface, the distance I am from the center is Re. R would be Re, or the radius of the Earth. And if I'm some height above the surface of the Earth, I'm Re plus h. So I plug that in here. So let's find out what that potential difference is. What is, if I call this 1 and this 2, what is U2 minus U1? Okay. Well, if I just plug in this for both those cases, I get a negative GMM over Re plus H, that's this one, minus a negative, so I'm going to get a positive, minus a negative, give me a positive, GMM over just Re. Okay. Well, that doesn't help me out too much, except if I did plug in some numbers there, I would end up getting the same thing as mgh, where I choose this to be my 0. Okay, let me show you how we can mathematically get there with a function. How can you get actually a function mgh and I have to just plug in numbers to check it? Okay, well, let's do something. This does require a math trick. Okay, I'm going to take a look at this first one. I get GMM. I'm going to pull an Re out of that denominator. And so it's going to be Re times 1 plus an Re times H over Re. Okay? So with that, if you just check it, Re times 1 gives me Re, Re times H over Re gives me H. So that's the same thing. I've just done a little math trick to pull it out. Okay, I've got to add this other term here. All right. Now, this right here is 1 plus a teeny number compared to a big number. Teeny number over a big number. That means this is a really small number. And we can do something in calculus called an approximation. And it's left for a higher level math class. But this term here, 1 plus h over Re in the denominator, is the same thing. Okay, so this is the same thing as 1 minus h over Re in the numerator. Okay, you can prove that mathematically when h is super small compared to Re, or the numerator is super small compared to the denominator. Okay, so you'll have to trust me on that one and look forward to a future math class to prove that. But when I look at this now, I get a negative GMM over Re times 1 plus a GMM over Re. Okay, well, those cancel, so that cancels with this. And I'm just left with this multiplied by that. And I get a minus, so it gives me a positive. I get GMMH, and I have an Re times an Re gives me an Re squared. But what is all that? What's everything but the M and the H? Remember from previous work, that is G. And this is nothing different than mgh, which is really, really useful when you're on the surface of the Earth, when h is super small compared to Re, which we've seen is true. And then we saw if you're not super close, or if you want to be super precise, well, we have to be careful about our distance. And we saw that we can get a new potential energy if we use an appropriate adjusted G. So both routes would come to the same conclusion. We can use our universal law of gravitational potential energy, or we can adjust G by knowing what it's defined to be and using the appropriate distance. Okay, so this is our introduction to gravitational potential energy.